When 15 supernova stars simultaneously erupt, synchronized in both time and spatial proximity, it generates an extraordinarily powerful explosion. Unsurprisingly, such a cataclysmic event fundamentally transforms the region of cosmic space where it unfolds. Interstellar dust is swept aside by the colossal forces of these concurrent explosions, leading to the formation of a monumental void composed of low-density matter. This also creates a shock wave that, to this day, continues to race through our galaxy at 6 kilometers per second. Following it is superheated plasma, with temperatures reaching 1 million degrees Celsius. This simultaneous Swiss cheese-like process, the creation of numerous voids, and the heating of the interstellar medium is now known as a hot bubble. It represents both an end and a beginning for stellar cycles. However, this isn't some distant structure hidden deep within the universe. Our solar system isn't even moving toward it. On the contrary, we are inside this bubble, rapidly approaching its original point of origin. This is our local hot bubble. Scientists now recognize it as the local environment surrounding our solar system. We are still actively exploring this region, but its nature is becoming increasingly clear. So what do we know about the local hot bubble? How did it form? And what more is there to discover in this amazing cosmic region? Today, we will delve into the aftermath of exploding stars and examine how scientists were able to determine that we are, in fact, at the very heart of this cosmic cataclysm. The local hot bubble was not always known to humanity. First identified in the 1970s through observations of low-energy X-ray emissions detected across the sky, the local hot bubble was hypothesized as a vast cavity in the interstellar medium, dubbed a superbubble. This cavity was thought to be filled with tenuous gas millions of degrees hot and extremely low in density. In the 1990s, scientists discovered that X-ray emissions could originate wherever neutral atoms interact with the solar wind. This called into question the initial idea that such radiation necessarily indicated the existence of a large hot bubble. But soon, new data conclusively proved that the hypothesis put forth decades earlier was indeed correct. In 2014, NASA confirmed the existence of the local hot bubble by studying diffuse X-ray emissions as part of the Local Galaxy Explorer mission, known as DXL. Although soft background emission can also come from other sources, such as comets, the mission found that only 40% of the low-energy X-ray fog originated from within our solar system. This confirmed that the dominant source was diffuse X-ray emission emanating from a region of interstellar plasma millions of degrees hot, known as the local hot bubble. While this confirmed the bubble's existence, questions remained open about what could have created such a massive void and what could explain the thousands of surrounding young stars. The prevailing answer turned out to be both violent and fascinating. Recent research indicates that the local hot bubble resulted from approximately 15 supernova explosions that occurred sequentially over several million years, erupting relatively close to each other. Scientists estimate that the first of these massive stellar explosions took place roughly 14 million years ago. Each one ejected immense amounts of energy, pushing away the surrounding interstellar material and heating the remaining gas to extremely high temperatures. Evidence of these ancient explosions is preserved in Earth's geological record, found in deep-sea sediments in the form of a special isotope called iron-60. This radioactive isotope can originate from several different sources, but supernova explosions are believed to be the most common source of iron-60. We know that the isotope source is extraterrestrial because Earth itself is incapable of producing iron-60. Furthermore, corresponding deposits have also been found on the Moon. What makes this radioactive isotope special is that its half-life is precisely known. We know it decays into cobalt-60, another radioactive isotope, before finally decaying into nickel-60, which is a stable element. Iron-60 is a valuable element for scientific inquiry. It has a half-life of 2.6 million years, while cobalt-60 has a significantly shorter half-life of only 5.3 years. Thanks to this characteristic, when deposits containing these elements are found, scientists can compare their concentrations, iron-60, cobalt-60, and nickel-60, using them as a kind of elemental clock. This allows for the precise determination of when the material was deposited on our planet's surface. Fortunately for the scientific community, international research teams have discovered several such significant deposits over the past 2 decades. In 2016, iron-60 deposits were found in deep-sea crust samples extracted from the Pacific, Indian, and Atlantic Oceans. These findings revealed 2 distinct peaks of radioactive debris, indicating a series of supernova events that occurred in the relatively recent cosmic past. Relatively close to our solar system, at a distance of just 326 light-years, samples showed an iron-60 peak between 3.2 million and 1.7 million years ago. A second peak was recorded between 6.5 million and 8.7 million years ago. Nuclear physicist Anton Wallner, who led one of the teams studying these deposits, noted that the distribution of more recent debris over 1.5 million years suggests a series of supernovae that exploded sequentially in close temporal proximity. Astrophysicist Dieter Breitschwert, who led a second team of scientists, identified the probable source of these supernova explosions, which he estimated occurred at a distance of 196 to 423 light-years from the Sun. These supernovae, which catalyzed the formation of our local hot bubble, were likely part of an aging stellar cluster. The surviving members of this cluster are now associated with the Scorpius-Centaurus Stellar Association. Using iron-60 deposits, the team was able to track the signals of 2 supernovae, one that occurred 1.5 million years ago and another 2.3 million years ago. These events resulted from the deaths of stars whose masses were 8.8 and 9.2 times that of our Sun, respectively. Remarkably, our local hot bubble continues to expand in size even today, albeit significantly slower than during the supernova explosions millions of years ago. Its expansion rate has stabilized at around 6 kilometers per second. In 2022, astrophysicist Catherine Zucker published a groundbreaking scientific paper that reconstructed the evolution of our galactic neighborhood. This work traced the chain of events that led to the formation of our local hot bubble and the subsequent formation of all the young stars we observe in its immediate vicinity today. Based on this research, an incredible discovery was made. Using data from the European Space Agency's Gaia telescope, Zucker and her research team constructed a 3D space-time map. This map clearly demonstrates that within 500 light-years of our planet, all young stars and star-forming regions are located on the surface of our local hot bubble. With these 3D coordinates and the 3D motions of stellar clusters, they were able to trace the history of star formation over the past 20 million years in the vicinity of our local hot bubble. The study's conclusions were unambiguous. All known star-forming regions near our solar system formed along the outer edge of the local bubble as it actively collected gas during its expansion. Stellar nurseries are a region where new insights are constantly being revealed, especially as our telescopes capture new images. Here is a stunning image of the Chamaeleon the Far Dark Cloud, one of our closest stellar nurseries, taken by the Dark Energy Camera on the Victor M. Blanco 4-meter telescope, located at the Cerro Tololo Inter-American Observatory. By studying the propagation of starlight from within this cloud, scientists can identify details of star formation processes, which, in turn, contributes to a deeper understanding of the local hot bubble's influence on our galaxy at the present moment. Starting from the birth of the local hot bubble 14 million years ago, Zucker and her colleagues identified 4 distinct epochs of star formation that occurred on the bubble's shell. Approximately 16 million years ago, the Upper Centaurus Lupus star cluster was born, followed by the formation of the Lower Centaurus Crux star cluster. Crux, or the local Columba Association, represents one of the key structures in our immediate cosmic neighborhood. These star clusters formed at a significant distance from each other, approximately 49 light-years apart. Notably, about 14 million years ago, these very stellar populations became the source of powerful cosmic explosions, supernovae, which are presumed to have initiated the formation of our local bubble. After the local hot bubble formed, 4 significant epochs of star formation were observed: The first, occurring about 10 million years ago, led to the birth of the Upper Scorpius Association and other older stellar populations. 4 million years later, or 6 million years ago, the second epoch of star formation gave rise to the Corona Australis constellation and older stars belonging to the Taurus constellation. Then, approximately 2 million years ago, in the third epoch, stars formed in the Lupus and Chamaeleon constellations, as well as younger stellar populations of Taurus and Ophiuchus. Finally, our current time belongs to the fourth epoch of star formation. In this epoch, we can observe dense star-forming molecular gas surrounding the local hot bubble. This gas will eventually become the building material for the birth of new star clusters that will appear along the outer edge of the bubble. Despite all this grand stellar creation, many might find it surprising that we are, in essence, cosmic outsiders. Our sun did not originate inside the local bubble. In fact, the sun was approximately 978 light-years away from where the first supernova occurred in the Upper Centaurus and local Columba associations. It only joined the local hot bubble about 5 million years ago, when its journey through the galaxy brought it directly into the bubble's confines. The trajectory, marked by yellow dots, clearly illustrates our sun's position just before it entered the bubble. And now, by sheer coincidence, our sun is almost at the very center of the local hot bubble. Drifting at the very heart of what was once a blazing cosmic furnace, scientists have shown significant interest in mapping the current temperature inside the local bubble. It's quite natural to wonder why we feel so comfortable if the plasma temperature here can reach 1 million degrees Celsius. The key to understanding this phenomenon lies in the plasma's density. As shown in the 3D map from Zucker's 2022 publication, our local hot bubble is depicted in dark blue. The density inside our bubble is extremely low. It contains approximately 100 times less hydrogen than the typical interstellar medium. Thus, although the temperature of this gas rises to about 1 million Kelvin, causing the diffuse X-ray emission we have observed across the sky, we have little to worry about. Tracking temperature readings within the local bubble has provided further evidence of its existence. An extended sky survey, performed using the eROSITA telescope, more commonly known as the eROSITA X-ray telescope, has gathered the most detailed all-sky soft X-ray emission data to date. This data was used to map the local hot bubble and our solar neighborhood in far greater detail than ever before. Launched aboard the joint Russian-German Spectrum Röntgen Gamma mission in 2019, the eROSITA X-ray telescope provided data that allowed a team of scientists led by the Max Planck Institute for Extraterrestrial Physics to create a 3D map of the local hot bubble and reveal a temperature gradient, with the galactic south being slightly hotter than the galactic north. This temperature dichotomy can be explained by supernova explosions that occurred in the last few million years. In creating this bubble map, the team also discovered that the local hot bubble is elongated towards the poles of the galactic hemisphere. This happens because the hot gas in the bubble expands in the direction of least resistance, which turns out to be away from the Milky Way's galactic disk. Along with determining the temperature variations and the bubble's shape, the team gathered this and other data to create an even more detailed map of our galactic neighborhood. On the new 3D map, our local hot bubble appears as a 3D blob, surrounded by and even overlapping with other galactic structures. These other structures represent known supernova remnants, such as the Gum Nebula, shown here in red, and dense molecular clouds, shown here in orange. With new data and 3D maps, these superbubbles appear to be widespread throughout our galaxy, creating a Milky Way that somewhat resembles Swiss cheese. The cavities of our Swiss cheese galaxy are carved out by giant supernova explosions, and new stars form along the edges of the holes created by dying stars. And, like Swiss cheese, it seems some of these superbubbles may have tunnels connecting them to other bubbles or structures, suggesting that our local hot bubble might be part of a complex network of similar formations throughout our galaxy. For example, we have the Canis Major Tunnel, which lies on the Milky Way's galactic disk and is believed to connect our local hot bubble to the Gum Nebula or another larger neighboring superbubble. However, the 3D map also revealed another previously unknown interstellar tunnel extending towards the Centaurus constellation, possibly connecting our local bubble to the nearby superbubble loop Y. While these interstellar tunnels are undoubtedly intriguing to the imagination, our current understanding of their nature and function is quite limited. Nevertheless, these extended corridors of hot gas and giant star-forming bubbles, created by the grand demise of massive old stars, evoke genuine admiration and demonstrate how powerful and deeply interconnected the evolution of our immediate galactic neighborhood truly is. This phenomenon vividly illustrates that stars are not merely born and disappear in cosmic isolation, but their colossal energy output continues to actively shape the surrounding environment for millions of years after their ultimate demise. And as our observational instruments and technologies become increasingly sophisticated and sensitive, we are gradually beginning to unveil the true scale and complexity of these cosmic structures previously hidden from our view. So, the next time you look up at the night sky, you might remind yourself that we are surrounded by amazing and complex cosmic patterns, like our local bubble in the Milky Way, which was carved out in space by ancient powerful cataclysms, and that some of the twinkling stars you see are actually located along the walls of a giant cavity formed by a supernova explosion, which, in turn, connects to other parts of our galaxy through mysterious interstellar tunnels. Imagine for a moment that you're looking out a window when a single dazzlingly bright light suddenly flares in the sky above you. This brilliant star shines as brightly as a full moon at night, perhaps even brighter, and is visible even in broad daylight. If you see this light, you might already be in serious trouble, as this suddenly appearing star is now filling Earth's atmosphere with a catastrophic dose of gamma rays and X-rays, irrevocably destroying our ozone layer and exposing us to the full fury of deadly solar radiation. And speeding towards our planet, ejected at 10,000 to 40,000 kilometers per second, is a cataclysmic wave of stellar matter and debris. Imagine the death throes of an exploding star, ejecting billions of tons of burning mass in our direction, ready to crash onto our planet's surface in a fiery tsunami. This phenomenon is called a supernova. Or at least, this is one possible interpretation of what we might observe if such an event occurred in our immediate vicinity. But how likely is it that this will actually happen? What does near us mean on a cosmic scale? How close must a supernova explosion be for life on Earth to be threatened? What would we, the inhabitants of Earth, actually experience in such a situation? And which stars in our neighborhood could explode in such a destructive manner? Today, we will discuss an event that could potentially be a true Armageddon in our lifetime, or merely a beautiful fleeting glimmer in the night sky. Let's start with the good news. Supernovae are not that common in our galaxy, the Milky Way. While astronomers observe hundreds of supernovae outside our galaxy annually, this is mainly a reflection of the colossal number of galaxies existing in the universe. Closer to home, however, in our own Milky Way, we likely see only 2 or 3 supernovae per century. This means the chances of one exploding tomorrow are not very high, but they are not impossible either. And, according to archaeologists, Earth has likely already encountered supernova explosions throughout its 4.5 billion years of existence. For starters, we are in a region of space known as the local bubble, a relatively sparsely populated region of interstellar space about 1,000 light-years in diameter, which is believed to have been carved out by a supernova explosion 10 to 20 million years ago, when our planet already existed. Scientists have found compelling evidence of another explosion that occurred 2.5 million years ago, thanks to high concentrations of iron-60 and manganese-53 isotopes in a specific layer of the geological record. This supernova occurred far enough away to be completely harmless to us. But this may not always be the case. Some scientists believe that the extinction of woolly mammoths was caused by a massive supernova fragment hitting the planet about 13,000 years ago. The site of the hypothesized impact contained magnetic spherules and radioactive potassium-40, a substance found in supernova ejecta. This was a kind of smoking gun in the era when most mammoths went extinct, Even earlier, tiny impact craters from grains of weakly radioactive iron, traveling at 10,000 kilometers per second, were found in 34,000-year-old mammoth tusks. If you recall, this was one of the potential speeds at which supernova explosions propagate. This certainly couldn't have been a pleasant experience for those ancient mammoths. However, a careful observer might notice a significant aspect. Evidently, if the origin of life on Earth occurred approximately 3.7 billion years ago, and over the past 20 million years, humanity has encountered 3 supernovae explosions that impacted us, yet life largely continues to exist. Sincere condolences, woolly mammoths, if your species did disappear due to one of these events. Then, on the whole, supernovae cannot be as catastrophic as presented in the introduction. And this assertion is largely true. However, it is certainly a matter of distance. If a person is 1,000 kilometers from a nuclear bomb explosion, they have nothing to fear. But a completely different situation arises if that bomb detonates on their coffee table. And when it comes to supernovae, it turns out the universe has relatively large coffee tables. To truly grasp the scale of these explosions, one must deeply understand the forces involved, which, in turn, requires a fuller comprehension of supernova mechanisms. As it turns out, there are 2 primary paths by which stars can reach this grand and explosive finale. However, in each case, an appropriate star is needed. The first path, leading to a Type Ia supernova, typically requires a white dwarf in a binary system that gradually or rapidly accretes matter from its companion star until it reaches a critical mass. This process is not fully understood, but it's believed that a white dwarf, a dense star composed predominantly of carbon in a giant super-hard diamond core, usually exists in a delicate balance between 2 powerful opposing forces, electron degeneracy pressure and gravity. This simply means that atoms generally resist excessive compression. Their electrons prefer to maintain certain distances from the atom's nucleus and will prevent compaction into a denser state. But gravity is an incredibly powerful force that tends to pull matter closer, especially in dense masses like a white dwarf, where a sugar cube-sized piece has the mass equivalent to a car. And in a binary system where the white dwarf absorbs more and more matter from its companion star, gravity eventually overcomes the electron degeneracy pressure, and the entire house of cards instantly collapses. Carbon fusion begins. Within just a few seconds, most of the star undergoes fusion, forming heavier elements and releasing colossal amounts of energy as the star's matter transitions into its slightly more efficient new configuration. How much energy is released? Approximately 1 quadrillion joules. This number represents a 1 followed by 45 zeros. If anyone claims to have known this number beforehand, they are almost certainly lying. All this energy is released in just a few seconds. Naturally, the star expels all its contents in all directions, sending it out at 6% the speed of light and releasing a flood of predominantly gamma radiation across the galaxy. The brightness of this event is 5 billion times that of our Sun, and it burns for several weeks until the ejected material has moved far enough away for the overall energy level to begin dissipating. The second type of supernova, type Tier-2, is similar, except that instead of a white dwarf, it involves a massive star at least 5 times the mass of the Sun in the final stages of its life cycle. These stars still burn brightly. And, in addition to electron degeneracy pressure, it is the heat from nuclear fusion that keeps the star in equilibrium. However, as with a Type Ia supernova, the equilibrium is eventually broken. This time, it happens because the star runs out of fuel. And without that extra fusion energy pushing the star's mass outward, electron degeneracy pressure alone cannot withstand the star's weight, leading to a similar effect. The only difference is that while a portion of the massive star will remain, often collapsing into a neutron star or a black hole, white dwarfs typically disappear entirely. Without a doubt, the scale of matter and energy released in a supernova explosion is truly colossal. This power is so immense that it's no surprise that any objects in the immediate vicinity of the catastrophe would not long survive. We are talking about energy capable of tearing an entire star apart. A planet caught in such striking proximity would not have the slightest chance of survival. Our Sun, fortunately, will never become a supernova, as its mass is insufficient for such an event. However, if it were to happen, there's a high probability that Earth would be either partially or completely vaporized. Its rocky surface would reach boiling point due to temperatures 15 times hotter than the surface of our Sun, and it would be carried away into space within weeks of the supernova's passage. Surprisingly, however, this initial destructive wave rapidly weakens with increasing distance. In fact, vaporization is not actually the most significant threat from a supernova. In 2011, specialists from Cambridge University conducted calculations showing that even planets orbiting their star at a distance of 15 billion kilometers, which is roughly 100 times the distance between the Sun and Earth, would remain intact. Instead, they would simply be flung into deep space as they would have nothing left to orbit. Of course, such a planet's hypothetical ecosystem would likely face other challenges. It would quickly become incredibly cold. Undoubtedly, even if a planet's crust remains intact, this by no means guarantees the persistence of life on it. Not to mention that the light of a supernova sometimes outshines an entire galaxy, leading to complete blindness for anyone who sees it. The mere destruction of our atmosphere would entail a host of problems. High levels of radiation, even if they don't directly affect us, would alter the chemical composition of our atmosphere, destroying our ozone layer. This would significantly increase our chances of dying from radiation sickness and cause mass extinctions as its effects ripple through the food chain. Scientists estimate this kill zone to be within 25 light years. Beyond this distance, the supernova's fury begins to subside as distance causes it to exhaust itself. While, admittedly, the asteroid that potentially destroyed the Mammoth came from a supernova 250 light years away, if it happened at all, it was likely a fluke. Generally, we would notice no damage from a supernova at such a distance. Its radiation levels would not be high enough to cause mass extinctions. At 500 light years, we would barely notice the event, other than perhaps a brighter star appearing in the sky. This leaves one important question. Are there any potential supernova candidates within 300 light years that we should be concerned about? Fortunately, scientists are quite confident that the answer is no. Massive stars are very conspicuous, and the only two that are at risk of becoming supernovae are Betelgeuse and Antares. Both are over 400 light years away. White dwarfs are a bit trickier due to their reduced brightness. They have been difficult to detect with conventional methods, making it hard to predict if we might be in danger from them. However, in 2013, the European Space Agency's Gaia Space Observatory released a vast amount of information as part of its star mapping efforts. This allowed scientists to identify 13,000 white dwarfs within 326 light years of us. Luckily, despite this large number, scientists remain confident that none of them are expected to explode anytime soon. Anytime soon means within the next few 100,000 years. Speaking of Betelgeuse, some scientists predict that this red giant could explode much sooner, possibly within the next few decades. Their research is based on the assumption that Betelgeuse has a significantly larger radius than previously thought. But if this assumption proves correct, it could mean that we might witness a local supernova in our lifetime. Of course, according to some existing cosmological models, we would have nothing to worry about in the event of such a cosmic cataclysm. A shockwave emanating from Betelgeuse would take a considerable amount of time to reach our planet, and even upon arrival, it would move with much less force than the usual solar wind pressure. In other words, our magnetosphere, or atmosphere, would not be the decisive shield. The protective shell of the Sun's heliosphere, which is a vast region of space where the solar wind dominates, would be more than sufficient to successfully contain the impact of such a supernova. So, there it is, the comforting truth. While supernovae may be some of the most massive and energetic explosions in the universe, by a fortunate turn of events, our part of the galaxy is safe from them. The probability that we will be affected even by nearby stars, such as Betelgeuse, that are destined to become supernovae, is incredibly low. Indeed, Earth has enough of its own cataclysms, such as devastating floods, powerful earthquakes, and crushing hurricanes, which can instantly bring devastation to any community, and space is still a dangerous and unpredictable place. But it's good to know that of all the things we have to worry about, we can probably confidently cross planetary destruction from supernovae off our list of potential threats. The universe is full of mysteries, and some of the most incredible ones are hidden just beyond visible light. What if I told you that over 1.5 billion invisible objects, from distant galaxies and newborn stars to some of the oldest luminaries in our entire galaxy, are just beyond our reach, veiled by dense cosmic dust? It's a bit frustrating to ponder, isn't it? However, that was only until recently. That's because, thanks to the European Southern Observatory's Visible and Infrared Survey Telescope for Astronomy, better known as VISTA, we can finally lift the veil on these hidden cosmic wonders. For the first time in human history, we have a fairly complete infrared map of the Milky Way that penetrates through the obscuring cosmic fog to reveal an unprecedented view of our galaxy and what lies beyond. Today, we will explore how this unique map was created and take a look at the stunning images that reveal previously unknown stars throughout our galaxy. In September 2024, VISTA published the largest and most detailed infrared survey of the Milky Way ever conducted, covering a 13-year period from 2010 to 2023, over 140 nights of observation. This massive project captured about 200,000 images and generated 500 terabytes of data. This is the same amount of data that would be needed to continuously stream 4K video for almost 3 years. VISTA is part of ESO's Paranal Observatory, located in Chile, and its primary task is mapping large areas of the sky. Using VISTA's infrared camera, known as VIRCAM, the team was able to peer through the dense clouds of dust and gas permeating our galaxy and discover some of the Milky Way's most hidden places. Traditional telescopes allow us to observe space in visible wavelengths, which range from approximately 380 to 700 nanometers. But VISTA is not like traditional telescopes. Instead of relying solely on visible light, VISTA operates at infrared wavelengths from 900 to 1200 nanometers, allowing it to detect invisible objects such as stars hidden by dust and cold brown dwarfs, also known as failed stars, which do not emit enough visible light to be seen with a traditional telescope. To get a sense of the differences between visible and infrared light, take a look at these two images of the Lobster Nebula, or NGC 6357. One is taken in visible light and the other with the VISTA telescope. We see that in the infrared, the dust obscuring our field of view seems to disappear, revealing hundreds of thousands, perhaps even millions, of previously unseen stars. The map was created as part of the VISTA variables in the Via Lactea survey, or VV-Phi, Via Lactea being the Latin name for the Milky Way, and its accompanying project, the VVV Extended Survey, or VVVVX. The data collected from these two accompanying projects, which comprise the VISTA Infrared Survey, have already led to the publication of over 300 scientific papers. Unlike other recent cosmic maps, this map is one of the most detailed ever created. It represents the first infrared survey to cover nearly 80% of the Milky Way's luminous mass, and it is simultaneously the largest infrared catalog of our galaxy's central region. This survey provides astronomers with a unique opportunity to study our galaxy in unprecedented detail. It gives us an accurate 3D view of the Milky Way's inner regions, which previously remained hidden from our view by dense dust. The survey covers a sky area equivalent to 8,600 full moons and contains approximately 10 times more objects than any previously published infrared map since 2012. Our Milky Way consists of a central bulge, a dense, bright, bulging collection of stars, surrounded by a flat disk with two spiral arms extending from its ends. The presented image demonstrates the region of our galaxy that was mapped during this survey. Red squares denote the central regions of the galaxy that were initially observed during the primary survey and then re-examined as part of the extended survey. Other colored squares indicate regions that were covered only by the extended survey. From this image, it becomes clear that these surveys focus directly on the central plane of our galaxy, covering part of the disk and a significant portion of the nuclear bulge. But what discoveries were made thanks to VISTA? Argentine astrophysicist Dante Maniti, who led the survey project, stated that they made so many discoveries that they have forever changed our understanding of our galaxy. While we'd love to tell you about all of them, it's probably wiser to focus on some key highlights. As part of a 2015 study, the VISTA telescope focused its attention on the Messier 20 star-forming region, also known as the Trifid Nebula, located approximately 9,000 light-years from Earth. When observed in visible light, this image shows a beautiful nebula, glowing pink from ionized hydrogen emission and surrounded by a blue haze of scattered light from young, hot stars. A cloud of gas and dust obscures the stellar space beyond it. Now, look at the second image, which was captured by VISTA's infrared camera. By peering past the clouds, we discover an entire cluster of new stars. This image not only allows us to see through the Trifid Nebula, but by a stroke of luck, it also revealed objects on the far side of our galaxy that had never before been seen. To their surprise, astronomers identified two faint reddened objects as Cepheids. Although they appear to be just beyond the edge of the Trifid Nebula in the image, they are actually very distant, about 7 times farther than the nebula that once helped obscure them from our view. Cepheids are a type of bright, unstable star. They brighten and dim over several days or months depending on their luminosity. The first variable star we ever identified in the modern era was Omicron Ceti, also known as Mira. It was described as a new star until 1638, when Johannes Hevelius observed it brightening and dimming in a cycle that lasted 11 months. As for this pair of newly discovered stars, they are the only Cepheids we have identified so far in this location, which is beyond the central bulge on the far side of our galaxy. And they can be extremely useful. They can be thought of as a kind of cosmic measuring stick that can be used at distances up to tens of millions of light years. If you know the duration of a star's pulsation period from bright to dim, you can deduce its absolute brightness as well as its age. You can compare the absolute brightness to the apparent brightness, that is, the amount of light reaching Earth. Thus, you have a measure of how far away the star is. With a few such reference points, we can build a true picture of the scale of our galaxy and beyond. Looking towards the very center of our galaxy, a group of astronomers and data scientists identified even more potential Cepheids, specifically 655. Subsequently, these stars were classified into 2 groups. It turned out that 35 of these 655 luminaries were classical Cepheids, representing younger examples of this type of star. This discovery caused genuine excitement, especially given the established belief that the galactic bulge primarily consists of ancient stars older than 8 billion years. By studying their pulsation periods, the team determined that all 35 mentioned Cepheids were younger than 100 million years, and some could be less than 25 million years old. For comparison, our Sun is approximately 4.5 billion years old. Thus, the youngest of the discovered Cepheids had existed for only 0.6% of our Sun's total lifespan. The Cepheid study conducted by this team culminated in another significant breakthrough. By mapping the 35 classical Cepheids they found, scientists were able to identify an entirely new structure in the Milky Way, a thin disk of young stars that permeates the galactic bulge. Hidden behind dense clouds of interstellar matter, it had remained unnoticed in all previous studies of this region. By discovering this structure, in conjunction with the identification of all Cepheids as mentioned, astronomers concluded that star formation has been occurring continuously in the galactic midplane over the past 100 million years. It is quite possible that there are other, even younger Cepheids that we have not yet observed, as such stars would be so bright that their image would be saturated in the VVV survey. The very fact of discovering this thin disk of young stars in the galactic bulge is truly incredible. Previously, it was thought that the galactic bulge was an ancient relic of our galaxy's past, where exclusively old stars formed separately from the stellar disk. However, this discovery demonstrates that the situation is not so clear-cut, and that the formation of new stars within the bulge may be a natural continuation of our galaxy's evolution. But even more inspiring, perhaps, is a discovery made during the VISTA infrared survey, located in the ancient heart of our Milky Way galaxy. In 2016, a type of ancient star known as an RR Lyrae, another variable star, was first discovered in the center of the Milky Way galaxy by a team led by astrophysicists Dante Miniti and Rodrigo Andres Ramos. This type of star is typically found in globular clusters, which generally orbit the outer regions of the galaxy. A globular cluster is a tightly packed group of tens of thousands to millions of stars bound by gravity. They are also very ancient, containing a stellar population that can be over 10 billion years old. The team discovered 12 RR Lyrae stars during the VVV survey, suggesting that they may be remnants of an ancient globular cluster right in the heart of our galaxy. This discovery also provides evidence that may help astronomers decide between two competing theories about how nuclear bulges form. While some scientists believe that the nuclear bulge forms early in a galaxy's evolution when several smaller galaxies violently collide, others say it forms gradually over time as gas is channeled inwards to trigger star formation. The detection of these ancient stars here suggests that the Milky Way's bulging center likely grew from the merger of primordial globular clusters, thereby supporting the first theory. Thus, this not only hints at the genesis of our own galaxy, but also offers compelling evidence of how these galactic bulges can form in other similar galaxies. Speaking of ancient stars, VISTA was able to discover 2 new globular clusters as part of the infrared survey in 2011. In this visible light image, the known globular cluster UKS1 can be seen on the right as a hazy red smudge. This cluster was the faintest known globular cluster before the new discoveries. Now compare the same patch of sky, but this time in VISTA's infrared light. Suddenly, we see what we were missing. Much fainter than the known UKS1, we can discern a second globular cluster, this time in the upper left of the image, which was named VVV-CL-001. Shortly after, another globular cluster was found, aptly named VVV-CL-22, and this small, dim group of stars may be the closest known globular cluster to the Milky Way's center. Did you know that before VISTA discovered these new ones, there were only 158 known globular clusters in the Milky Way? In the current study, the discovery of 2 more such unique stellar objects represents a highly significant achievement in astronomy. In the central part of the galaxy, young stars and clouds of cosmic dust easily obscure globular clusters, especially given that their relatively old age prevents them from emitting sufficient light. However, now that these clusters have been discovered, they open exciting avenues for further study. It might just be an optical illusion related to perspective, but scientists are actively discussing whether a gravitational link exists between VVV-CL-001 and UKS1. If this link is confirmed, they would become the first known pair of binary globular clusters in our Milky Way galaxy. It should be noted that similar binary clusters have already been discovered in other galaxies, such as Centaurus A and the Large Magellanic Cloud. Specialists believe that it is through the collision of these gravitationally bound clusters that the most massive globular clusters, such as Omega Centauri, form. Thus, studying a binary cluster directly in our galaxy could provide invaluable data and amazing insights into this process. At this stage, these are only hypotheses, but the idea itself certainly sparks great interest for speculation. Beyond globular clusters, the VISTA infrared survey revealed many other types of star clusters. At least 96 new open or galactic clusters were found, which typically contain fewer young stars and are much more common than globular clusters. Like globular clusters, they were hidden behind a veil of cosmic dust, but VISTA's 4.1-meter infrared telescope lifted this veil to reveal them in all their glory. Just take a look at some of these stunning images that are now available for study. One such open cluster, VVV-CL-003, is much harder to discern in images compared to tightly packed globular clusters. Try to find differences in star density in this part of the image compared to the surrounding areas. It was discovered by the VISTA telescope 15,000 light-years behind the center of the Milky Way, and is also the first of its kind found on the far side of the galaxy. The colossal scale of this survey is truly astounding. Covering a vast area of the sky and mapping over 1.5 billion objects, this data has already led to fascinating discoveries that are rewriting our understanding of the Milky Way and beyond. And this is just a fraction of what there is yet to learn. This survey will serve as a robust foundation for future telescopes and observations, which, we hope, will build upon VISTA's legacy with even higher resolution and sensitivity. We now have the most detailed 3D map of the Milky Way's structure and objects ever created, a map revealing hidden wonders previously inaccessible to our study. And scientists are already actively uncovering new galactic features and reshaping our understanding of the galaxy. With the information gained from this groundbreaking infrared survey, as well as the recent work of the European Space Agency's Gaia mission in visible light, it is a truly exciting time for astronomers, and we can confidently expect astronomers and data scientists to continue uncovering new mysteries thanks to VISTA's 3D map. VISTA's infrared observations have revealed dozens of hidden star clusters and millions of previously unseen stars. They have discovered new stellar nurseries where stars are born and expanded our understanding of the Milky Way's formation process. Looking at the sky through different wavelengths has led to a new era of galactic exploration, and we can expect astronomers and data scientists to continue uncovering new mysteries thanks to VISTA's 3D map. Friends, thank you for watching. Don't forget to subscribe to the channel and like our content if you enjoyed it. See you in the next video.